It was mentioned previously that the panels in Simpson's rule are parabolic arcs, second-order curve, as opposed to the line segments in the trapezoid rule, which are first-order. This is consistent with our earlier explanation that 3 data points are needed to uniquely describe a parabola, as opposed to only 2 for a straight line. Notice that my data points are evenly spaced. x0 is h units to the left of x1, and x2 is h units to the right of x1. The red curve is a second-order polynomial. We don't know the coefficients of a, b, or c just yet. Setting x1 equal to 0 is basically what was shown graphically on the previous screen. x0 is equal to negative h, and x2 is equal to positive h. y0 is a function of x0. Let's substitute x0 equals negative h. Now y0 is expressed in terms of h. Same idea with x1 and y1. This one is simpler because 0 cancels out 2 terms. y2 looks almost identical to y0, with the exception of a minus sign. The past 3 slides are summarized here. We have y0, y1, and y2 expressed in terms of h and the unknown coefficients a, b, and c. Notice that y1 is equal to c. We can substitute that into the expressions for y0 and y2. This is the result. Now I just move all the y's to the left-hand side of the equation. If I add the 2 lines together, I get this result. So effectively, I've solved for the coefficient a in terms of mesh size h and function values y0, y1, and y2. I'm going to leave it in terms of 2ah squared. You'll see why I did that very soon. Remember that we are trying to find the area underneath that parabolic curve. Area can be represented by a definite integral. So here's the definite integral of the parabola from x0 to x2. Pause the video if you wish to peruse the details. Otherwise, notice the last line. This expression for area has 2ah squared in it. So now it's just a matter of substituting what we already know. By combining like terms, we are left with the expression in the last line. This is in fact the very same Simpson's rule we derived from the Taylor series earlier. We have just shown an alternate derivation, starting with the assumption that each panel is constructed with a parabolic arc. If you remember the first slide, one panel didn't fit the curve very closely. However, 2 parabolic arcs give us a closer fit to the blue curve. Just like we saw before with other methods, decreasing the mesh size h is often a good way to improve the accuracy of our approximation. Decreasing the mesh size is equivalent to increasing the number of panels. I should have mentioned it before, but this strategy results in what is called a composite rule. Composite because it is made of many separate panels. We've seen this already for 2 panels. Same idea for 3 or 4 panels. Notice the 2 sandwiched between the 4s. So the pattern alternates 4, 2, 4, 2, 4, etc. Also notice the last term for each composite rule, y2, y4, y6, and y8. Each subscript is an even number. That is one important restriction when using Simpson's rule. If the subscript n were odd, we would not be able to use Simpson's rule as is. We could deal with that situation, but it would involve some tweaking. For all the examples shown thus far, I have constructed data tables deliberately in order to avoid this situation. The pattern of alternating 4s and 2s can be generalized and represented like so. Again, we have seen a more thorough derivation of Simpson's rule using the Taylor series. I just wanted to link that to the fact that Simpson's rule is the result of using a parabolic arc in each panel. So if line segments yield the trapezoid rule, and parabolas yield Simpson's rule, what do you expect we will get from cubic arcs? Feel free to speculate in the comment section below. Otherwise, If you want to know the answer to that question, stay tuned for the next lesson.